I'm going to talk about convergence analysis of steepest descent algorithm for Wiener filter. Previously in this channel I talked about Wiener filter and steepest descent algorithm. Now I'm going to continue with convergence analysis. Before that I will have a summary from that video. As you know, the framework for adaptive algorithm is we have a filter or linear combiner with the weight vector W, input data, it's a vector m by 1, and a desired signal dn, and the output of filter yn. We would like to opt or find W in a way that D be close to Yn. In a perfect way, we want the output of filter equals to desired signal. Actually, we have a linear estimation of desired signal based on the input vector. Okay, we will have error. And here we have a weight control mechanism or adaptive algorithm based on an up-to-date rule. We change W until we reach the optimum solution. The natural cost function for finding W is mean square error. Mean square error is our cost function. So I can write JW equals to expected value, absolute value error squared. And the input-output relation of filter is Yn equals to W Hermitian UN. This is the input-output relation for a beamformer spatial filter or temporal filter. Any filtering or convolution we can write in a vector and matrix form like this relation. If I put the relations, we will have JW equals to absolute value desire minus Yn. Yn is W Hermitian UN equals, and I can write this dn minus W Hermitian UN and take conjugate or conjugate transpose Hermitian. From this we will have d conjugate n minus U Hermitian W. If we multiply these two terms, I will have form terms. I can write them here. Sigma squared d minus W Hermitian P minus P Hermitian W plus W Hermitian R W, where R is the correlation matrix of the input vector. It is expected value UN U Hermitian, and P is the cross correlation between desired signal and input vector. Expected value UN DN conjugate. This is my error performance surface, and for finding optimum solution I can take gradient and set it to 0 to find optimum weight vector. If I take derivative JW, which I call it G, and we will have minus 2pw plus 2rw equals to 0, then I will have w optimum r equals to r inverse p. This is the optimum weight vector, and we call it Wiener filter. But R inverse of a matrix is computation of the inverse of a matrix is so costly, and there are many problems and instabilities, and this is not something good for someone that would like to implement the algorithm. Actually, we should avoid inverse correlation matrix. So we use gradient descent, and we use adaptive algorithms to find W optimum. Gradient descent algorithm, W new equals to W old minus step size or learning rate, the gradient vector G in actually Wn, or minus mu over 2. It's not something important. We can take all of this term as mu. If we put G in this relation, we will have a steepest descent algorithm. For Wiener filter, we have Wn plus 1 equals to Wn plus mu p minus r Wn. This is the up-to-date rule for a steepest descent algorithm. And I'm gonna assess the convergence. I'm gonna do convergence analysis for this relation. What do I mean by convergence analysis? I am gonna show if in after time passing, when n goes to infinity, if we will reach to W optimum, or what are the conditions, what mu should be, for example, to reach to W optimum, and the rate of convergence is also important in this analysis. I can rewrite this up-to-date rule. I can write it like this: I minus mu r Wn plus mu p. Why we have convergence problem? As you see, there is a feedback here. This is a recursive equation, and we will have feedback. For example, if this is Z inverse I, this is Wn plus 1, here we have Wn, and Wn multiplied by I minus mu r and add with mu p give us Wn plus 1. As you see, here is a feedback, and feedback can be source of instability. So we should find the conditions that guarantees our algorithm is stable. Let's continue and find the conditions for a stable algorithm. I multiply minus 1 to both sides of this equality. I can rewrite this minus Wn plus mu r Wn minus mu p, and then add W optimum to both sides. W optimum minus Wn plus 1 equals to W optimum minus W1, and plus is, if I take mu r, we will have Wn minus r inverse p, which is W optimum. I call this, I name this Cn plus 1, so I have Cn plus 1 equals to Cn minus mu r Cn equals to I minus mu r Cn. In this form now we have a homogeneous recursive equation. That algorithm we have actually mu p here, but here there is no input for this equation. And let's continue. I use normal form for R. Normal form for correlation matrix equals to Q lambda Q Hermitian. Q is the eigenvectors and lambda is the eigenvalues of our correlation matrix. I put normal form here, and we will have, we also have Q Hermitian Q equals to I. It means Q is an orthonormal matrix. Cn plus 1 equals to I minus mu Q lambda Q Hermitian Cn. Multiply both sides from the left with Q Hermitian. So we have Q Hermitian Cn plus 1 equals to I minus mu lambda Q Hermitian Cn. I name this Vn. Here Vn plus 1, and here is Vn. And finally we reach to this equation, Vn plus 1 equals to I minus mu lambda Vn. What is the benefit of this relation? Lambda is a diagonal matrix, so I can separate every mode in this algorithm. We have, for example, Vk n plus 1 equals to I mu minus mu lambda k Vk n, for k equals to 1 to until m. This is the natural mode for our adaptive algorithm. And these are so simple to talk about because it's a scalar and they are separated, so I can solve it based on the putting, for example, starting from putting 0. For example, we have Vk1 equals to 1 minus mu lambda k Vk sef. Then Vk2 equals to 1 minus mu lambda k Vk1, and if we substitute here, we have a squared Vk0. if we continue this, we will have vk n plus 1 equals to 1 minus mu lambda k power of n vk 0. This is the behavior of our actually mode, and as you know, based on the change of variables, we had Vn equals to Q Hermitian W optimum minus Wn. If we want to reach W to W optimum, it means Vn must be 0. Vn, there is it's like this: Vk0, 1 minus mu lambda k, Vk0, and so on. Actually, this must go 0. We should have Vn equals to 0. And this is a series, a geometric series, so the geometric radius, absolute value 1 minus mu lambda k must be lower than 1. And if we solve this equation, we will have learning actually rate or step size must be between 0 and 2 over lambda k. If we want to have an intersection between all m domains, we can write it. The intersection is between mu between 0 and 2 over lambda max. And finally, if I want to discuss about the speed and the convergence rate, we have this curve. Actually, it's Vkn equals to Vk0, 1 minus mu lambda k power of n. I'm gonna fit an exponential to this curve, and it's like a curve for discharge of a capacity. We will actually fit Vk0 e minus n tau k. Tau is the time constant or for the algorithm. If we, for example, put n equals to 1, we have 1 minus mu lambda k equals to e minus tau k, and take ln 1 minus mu lambda k equals to 1 over tau, and tau equals to minus ln minus lambda k. And as you see, the convergence rate and speed of the algorithm is based on the step size parameter and eigenvalue spread. And for large mu, we have a high convergence rate, but for a small mu, we have a slow algorithm. We reached to the end of this video. I hope you enjoy it. Please subscribe my channel to see more videos regarding signal processing topics.